In this video, we're going to find the trigonometric value of all 13 sides of this figure, and in the process we'll be able to prove a couple of multi-angle identities for sine and cosine. So we'll start with a right triangle that has an angle alpha and a hypotenuse of 1. We'll create another right triangle that has an angle beta. Next, we'll add an additional line on this pair of triangles. Starting in the upper right-hand corner and moving down to the second hypotenuse, we'll create a line that's perpendicular with that second hypotenuse. And that will give us 13 lines, the trigonometric value for each that we're trying to find. So let's name those sides so that they're easier to refer to. Around the outside of the triangle, we have 1, 2, and 3. And then 2 is composed of 2a and 2b, and 3 is composed of 3a and 3b. The diagonal line that we created earlier will be side 4, and 4 is made up of 4a and 4b, and the shared line of these two triangles will be 5, made up of 5a and 5b. So there's our figure. Now one thing to note here is that although side 1 is equal to 1, the other hypotenuse of the lower triangle is not necessarily equal to 1 because beta might not be equal to alpha. We'll make one other note about the angle beta. Since this is angle beta of this triangle, the other angle in that triangle must be 90 minus beta, and because that angle is shared in another right triangle, we can see that this angle must also be beta. Now because of the extra line we drew in this figure, we can see that the value for 3a will actually be equal to cosine of alpha plus beta, and the value for 4 will be equal to sine of alpha plus beta. Now, of course, we don't know what these values are yet, and we don't want to use alpha plus beta. We want to be able to specify the length of those sides in terms of trigonometric functions that operate only on alpha or beta, but not both. So those will be the two identities that we find. Now, moving on to those values, we can see, because this is a right triangle with a hypotenuse of 1, that side 2a is simply sine of alpha, and side 5 is cosine of alpha. Building on that fact and working on the upper right-hand triangle, if 2a is sine of alpha, 4a would then be sine alpha divided by cosine beta, and of course dividing by cosine beta is the same as multiplying by secant beta. So 4a is sine a secant beta, and using that as the hypotenuse, we can see that 5b is just a side opposite an angle beta. So given that fact, we can see that the side opposite angle beta would have a value of sine alpha times tangent beta, because multiplying sine of beta times secant of beta is the same as dividing sine of beta by cosine of beta, which of course is just tangent. Next, we'll use the fact that side 5 has already been determined to be cosine of alpha, and so using this right triangle, we can see that the hypotenuse would be cosine of alpha divided by cosine of beta, otherwise written as cosine of alpha times secant of beta. And then multiplying that hypotenuse times sine of beta would get you the value of the opposite side, which would just be cosine alpha tangent beta. Again, as sine of beta times secant of beta is the same as sine of beta divided by cosine of beta, which is just tangent of beta. We can then add 2a and 2b together to determine the value of 2, which would be cosine alpha tangent beta plus sine alpha. Having determined that 5 is just cosine alpha and 5b is sine alpha tangent beta, we can subtract 5b from 5 to get 5a, which would be cosine alpha minus sine alpha tangent beta. Using that as the hypotenuse of this triangle, we can multiply that by cosine of beta and see that 3a would be cosine of alpha cosine of beta minus sine of alpha sine of beta. And as we determined earlier, 3a is in fact the same as cosine of alpha plus beta, so that gets us the identity cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Now returning to the fact that we've determined that side 2 is cosine alpha tangent beta plus sine alpha, we can use that as the hypotenuse of this right triangle and determine that side 4 would simply be side 2 times cosine of beta, which is to say that side 4 is cosine beta times the quantity cosine alpha tangent beta plus sine alpha. And as we earlier determined that side 4 would in fact be the same as sine alpha plus beta, we see that we have another identity, specifically sine alpha plus beta would be equal to sine alpha cos beta plus cos alpha sine beta. And then returning again to the hypotenuse, represented by side 2, we see that 3b would be sine beta times the quantity cosine alpha tangent beta plus sine alpha. So we do that calculation, and it becomes cosine alpha sine beta tangent beta plus sine alpha sine beta. And now that we've got side 4 and 4a, we can simply subtract 4a from 4 to determine that 4b would be sine alpha cosine beta plus sine beta cosine alpha minus sine alpha secant beta. And that's all 13 of the sides, including the 2 identities for multiple angle formulas. And here's a table of all of those values. So I hope you enjoyed the discussion of this figure with multiple angle values and trig identities, and thanks for watching.